Hello, welcome to class number 8, and today we will be working on a practical example doing a fluid simulation, and here is the like a quick preview of what we're gonna be accomplishing today. We will try to cover entire subject within this class, and if we won't fit into the class recording time, then we will continue finishing this project next class. Okay, so there are 4 fields involved into this simulation, such as the density, temperature, velocity, and the fuel. And the geometry that is being animated is taken from my motion capture preset. You can find it by going to C drive and then program files and Autodesk and such, and under preset folder you would be able to see the several motion capture examples. And what I did, I took let me open the file. So what I did is I selected the piece of geometry, and I exported it as a Alembic file, edited UVs, and then I baked the texture. So before we go into the details of how this particular effect was achieved, let's just review in more details the fluid fields. Since there are 4 of them involved, we need to make sure that we fully understand the concept behind of the fluid fields. And here I put a little example, simple example, and let's just recreate the same setup I have here. So what I did first is to select camera and change the focal length from default 0 to 100. This way we would avoid the parallax when comparing 2 or 3 different fluid containers within the Maya viewport. Then we go to fluid, create container with emitter, and you just reset settings to default, hit apply, and you'll get the already familiar to us a fluid container with the emitter parented to it. We could observe that in outliner. So this is our fluid container, and this is an emitter. So the first thing I like to do is to unparent the emitter. This way, when I transform the fluid container, the emitter does not follow. I select the fluid container and uncheck keep voxel square because I'm gonna modify the settings by myself, and I change the size from 10-10-10 to 10-30-10, so it's longer along y-axis. And I also change the size resolution by multiplying size by 3, multiplier 3, which would result to 30, 90, and 30 again. And then I go ahead and under display I choose a bounding box because I don't want to see the voxels representations. I turn particles to off as a wireframe display. Under high detail solve all grids. This is my preferred way to deal with the fluid simulations. You might want to, if you have a slower machine, use off for high detail solve, but I highly recommend choosing all grids because it delivers much better fluid simulation qualities to it. Under shading, I click the color swatch transparency and change the default 0.25 to 0.05, so it's barely transparent. Okay, so now if I select the fluid emitter, we want to change the emitter type to volume, and under the under the volume emitter attributes, change it to torus. And you also might want to change fluid drop-off attribute found under the fluid attributes to 0. That means the emission of that coming out of the emitter will be uniform from boundaries to the center of the emitter. So we move the emitter down, and we're practically ready to start that simple simulation. Before we do that, let's select the fluid container, going into the dynamics properties, and we want to change the boundary to bounding x to none, boundary z to none, and y-axis to -y. Okay, so let's play back. And it's quite boring. Let's right click on a timeline and say playback speed to play every frame maximum real time. Select fluid container, and to make things more entertaining, let's change under the dynamic simulations, simulation rate scale, instead of 1, type 3. So we've got 3 times faster simulation. So we don't have to wait for that long. So what we see here is a basic, practically default simulation that happens as a result of density and velocity. So if we turn off, so currently having 2 grids, let's call each of these content methods as a grid. So we would say that having a density set to dynamic grid and a velocity set to dynamic grid, we would have 2 active grids within one fluid container. So we could imagine this as a single fluid container that being represented to us as a box has 2 exactly same grids inside, which are blended or merged together. And those grids, as we know, could be easily visualized by going into display and say full. So that's what we see here is two grids. One is density and one is a velocity being overlap on top of each other. Unfortunately, we're not able to select, for example, density grid and move it to the side, leaving, let's say, velocity grid behind. By other words, it would be quite an advantage to be able to separate, for example, the density grid from velocity. So you would theoretically reposition velocity grid, scale it, rotate it, give it different qualities, attributes independently on the density, and vice versa. Every time we turn off one of those grids, we kind of turn off the simulation that will be run inside of that grid. Density itself has got attributes that we already know listed under the density tab, and the velocity grid has got its own small attribute area that's responsible for controlling what's happening within velocity grid. While it's kind of clear that the different grids are practically independent entities, they are blended and merged together, giving us a combined result of simulation. So let me turn off the boundary so we only see the bounding box. And once again, when I play back this simulation, all we see right now is a result of the density and the velocity, or combined result of two simulations, density and the velocity. So if I would turn temperature on, I would add another grid, or turn on third grid within the same container. Now the result of this simulation would be a combined of simulation that runs in 3 grids. That's actually, if we open, if the concept of having 3 different grids, and once again, to make this visually understanding, this is our grids. So if I would turn the temperature grid, we kind of add third grid to already pre-existing density and velocity grid. But since they overlap and we're not able to see them independently, and since we're not able to separate and move them away from each other, we also kind of fool that whatever happens inside of the fluid container happens in the same grid. In order to illustrate this concept even further, we have under the fluid shape attribute editor, we have a grid cache tab, and this tab is being used after the simulation is being cached on a hard drive. And by selecting or deselecting those checkboxes, you instruct Maya to read or not to read the fluid cache from a hard drive for a specific field or for a specific grid. Field and grid are 2 terms that interchangeable. And this is one of those rare occasions when within the fluid attribute editor we're able to see the separation between those grid entities. So anyway, I just would like to make sure that everyone understands that whatever happening inside of the fluid container is a result of not a single simulation that runs inside of it, but combined averaged result of the multiple grid simulations. And as there are as many grid simulations running inside of the fluid container as the many of them selected under the content method. So once again, for this particular example, we only using density and a velocity. So if I would play back this thing, the result is quite evident, and now we're ready to proceed to comparing this simulation to temperature. What would happen if we would add a temperature? If I would switch the temperature to dynamic grid, we will be not able to have a visual representation of the difference before and after. So in order to be able to see the difference, what difference the temperature grid would do to the simulation, I select the fluid container and on a keyboard hit Ctrl C like copy. And then I, just like in the Word editor, I Ctrl V and I just copy pasted entire fluid container into my simulation. So once again, if I delete this copy pasted thing, so if I delete whatever existed there, so I have a fluid container here and fluid emitter. I select the fluid container, Ctrl C, Ctrl V. And when I Ctrl V or paste, Maya automatically groups the pasted content under the group. So I can select that group and move the just pasted container to the right. So as a result of this simple manipulation, I have two duplicated copies of two containers. Of course, I could just select the original container and duplicate it. But in order to duplicate it with it remembering the relationship with its own emitter, I would have to go to advanced duplicate settings or even use a hypershade to check option to duplicate the incoming connections. So there are much more things to do instead of like just a copy and pasting. So I select the first container and I change its name from a fluid to density fluid. And I also change the emitter name from a fluid emitter to density fluid emitter. And I ungroup this thing that we just copy pasted, and instead of the pasted fluid I say temperature fluid, and I would do the same for the emitter. So we're able to say what is what. Okay, so on the left, the container that we created originally driven by density and a velocity grid simulation, and then on the right it's a duplicated copy of it. So let's the reason why we now it becomes more evident why we would use a focal length of 100, because now we kind of almost in the orth view. So seeing both containers side by side, we kind of avoid parallax effect that might result to us to believe that the simulation that runs within those containers is different. So we selected the second duplicated container, and we, under the density, we choose off, and instead of density we will turn dynamic grid for the temperature. Under the display settings, shaded display, we turn temperature on, and for the first original container we choose the density. So the first container shows us a density, the second container shows us temperature. Select the container once again, and opacity preview gain, change it to from 0.5 to 0.9, so we can see more like a denser representation. And same thing for the second container, 9. Okay, so now Select the fluid emitter for the second duplicated container, and under the fluid attributes, change no emission for the density and say replace for the heat emission and set it to 1. Turn fuel to no emission, which does not make any difference to this simulation because the fluid container has got fuel dynamic grid turned off. We also select the first emitter, the original one, and we change replace for the density method emission, and for the heat we turn off, and for the fuel is off. So the reason why we choosing replace method for the emission is because it's a guarantee that both emitters emit exactly same value into the fluid container. Well, add would do the same thing, but replace is kind of more easier to understand. Okay, so shaded view by hitting F5 in the keyboard and play back the simulation. So let's select the temperature fluid emitter or temperature fluid container, the one that we duplicated. Go under dynamic simulation, turn gravity to 0. Not that it will make any difference because as from previous classes we know that the gravity attribute change affects only the density simulation. The density tab for this particular container, as we can see, is all grayed out because we turn off the density grid. And under the temperature, let's change the default dissipation value to 0, diffusion to 0, and turbulence to 0. And we set buoyancy. As we know, buoyancy for the temperature is nothing else but gravity. So buoyancy for the temperature is 10. And now select the container that runs only density simulation. And under the gravity field, change it to 10. So density container is driven by gravity attribute, while the temperature container is being driven by buoyancy found under the temperature attribute. Okay, so now if I play back simulation, we would be able to see that simulation that runs with inside of those two containers are identicals. So once again, one container is a temperature on the right, okay, here, and one container is a density, both using completely different scenario. I mean, completely different attributes found within the attribute editor. But what we're able to prove here is that density and the temperature inside of the fluid container are nothing else but just a duplicated copy of each other. So there's no really temperature as it turns to be. All the same algorithm baked into the same tool and given to us in duplicated form. One is called to be a density and one called to be a temperature. The only difference between those two simulations is that gravity, for example, as we already covered, driven by gravity, density is driven by gravity attribute that is being multiplied against density buoyancy attribute. So changing, for example, buoyancy to 10 and gravity to 1 would give us exactly same look. So both just it's the same attribute, just placed in different locations within the fluid attribute editor. So I hope that, and once again, the gravity only affects the density. It's got no impact on the temperature. So once again, here on the right, we have a simulation that only utilizes the temperature and the velocity. So if I would turn the gravity field to like any number that I could just type in, like you can see it makes no difference on the temperature simulation. And once again, when we say temperature simulation, it's got as much temperature simulation in it as much as density, by my opinion, because they're all the same. And now, under the temperature tab of the second container that is being driven by temperature and a velocity grid, we have one extra attribute that is called to be a turbulence. If we select a density container and look at the density tab, we can see that the only difference between this container here, let me just a copy tab. So this attribute editor represents the temperature container on the right. This attribute here represents density. So I duplicated so I could just put them side by side. And here on the content method, I displayed density, and here content method content detail, sorry, it's called. I select temperature. So as we can see that the temperature has got the turbulence attribute, while the density does not have it. So that's one of the main reasons why sometimes I want to use the temperature, is to get the access to the turbulence attribute. And the turbulence attribute is quite simple and sometimes quite brutal too, because it's not really physically accurate fluid simulation. All it does is just injects random velocity vectors into the fluid container. And sometimes it's kind of important to have that look, but most of the time could be avoided. All right, so now we have practically, not practically, but identical simulations running with the density and the temperature. So let's now just select a container. It doesn't matter which one. I select the temperature and I Control C. Let me open that outliner, and I Control V. So I paste it once again, third container. I move it to the side, and this container, let's select the group, say ungroup, and let's rename it fluid density and temperature fluid. Okay, and I do the same for the emitter. I rename it. So now I have three containers. First is density only, second temperature, and the third one, I go ahead and turn on density to be a dynamic grid. Here, if I would hit playback, I'm still will be only seeing result of the temperature only, because in order to be able to benefit from a density as well, I need to turn the fluid emitter to density replace 1. So now third fluid emitter emits density and temperature, and fluid container, third fluid container, has got density velocity, and temperature grid all turn on. So first one has got only density, second only temperature, and the third one has got both density and temperature. So if I would start playback, I would imagine that the third container that's got both density and the temperature turned on should look kind of different to what we have on the left. But surprisingly, not a big of the difference. There is a little bit of something different. It kind of accelerates a little bit faster, but not as much as twice, for example, faster. And that's because of the fact is that the result of the simulation is averaged to each other, meaning like of temperature and the density, they merge together, delivering one single result. So they're not, as I understand, they're not additive. If there is some kind of additional calculation involved behind of how multiple grids, such as a density and temperature, are given to us, this is not as simple as a density plus temperature. So I think they first evaluated, run, then summarized together, and the only way to build idea what combination of those multiple fields results to is to run simulation and compare. So that's little introduction into the grids of the fluid container should give us a clear understanding of what the grids are and how they work together. The last grid that built into the fluid container is called to be a fuel. So for the fuel, I made a quick example. So this is same fluid container that we were playing with, except it's got a fuel turn on, and the emitter's got fuel method set to replace, just like heat and density. And I put like a few keyframes here, and in order to illustrate the thing, I just mute those keyframes for now. Mute selected, select the second one, and say mute selected too. So by muting the keyframes, I practically canceled any animation. So it's consistently one through the entire frame range. And the display method for this container, once again, that runs density, velocity, temperature, and fuel, set to show temperature only. So if I play back the simulation, you would see that the temperature goes up and it dissipates rather quickly. If I stop simulation and under the display show fuel, and we can see that there are a lot of fuel being emitted from a fluid emitter. And the reason is I want to show this example is to illustrate the concept of what the fuel is doing inside of the fluid container. One of the major attributes for the fuel is called to be heat release. It could be called a temperature release instead of heat release, because we're dealing with the temperature here, not with the heat. And heat and temperature are those two terms used within the fluid attribute editor that means the same thing. So heat release or temperature release attribute controls how much temperature the fuel releases or emits into the fluid container. And the reaction speed is the attribute that controls how fast this emission happens. Or by other words, it could be just a multiplier to heat release attribute. As a matter of fact, I would say that those two attributes probably are multipliers again. And what they do, one cancels another or multiplies to make it larger. Okay, anyway, but what I would like to make clear with the fuel grid, and this is a grid we're dealing with, is that if we would visualize fuel like we're visualizing now, and it does not look in OpenGL viewport any different from a density, is that the main purpose of the fuel grid is to emit a temperature where from the voxels where the fuel is being presented. So if I would just turn on display, let's say instead of bounding box to full, and zoom in into this fluid container, I could clearly see that. And since we're displaying right now fuel, then I would say that by changing the attributes for the fuel attributes, by changing the fuel attributes, I only able to control how much temperature will be emitted into the voxels that already populated with the fuel. So in this view right now, we see that, for example, voxel here does not have any fuel inside. So by changing these numbers here, I'm not really modifying how much temperature will be emitted here. But this voxel here is definitely being populated by the fuel. And by changing the fuel attributes of the fluid container, I will be modifying how much temperature will be emitted into this fluid voxel from this particular fuel value here. So another way to explain this, or another attempt to explain this concept, is to mention that imagine that the fuel is like, we have this very familiar geometrically shaped fluid emitter, like a torus, and it's called to be a volume emitter because it's got shape to it. So what the fuel is volumetric emitter that emits temperature, and it changes, instead of like being locked to geometric shape like here with the torus, we dealing with the constantly changing substance of the emitter. So fuel is nothing else but a grid that is being used or that serves within the fluid container as a fluid emitter. But instead of like calling it just a fluid emitter, it emits temperature. It's not able to, for example, emit density into the fluid container. It only emits a temperature. And as we already discussed it earlier, temperature itself, while can be used for rendering purposes if you would change the under shading attribute, then because we're able to select what field or what grid we would be using for the opacity, for the color, and such, for incandescency. Not really useful for, I mean, not, it is useful, but the main purpose of the temperature grid is to drive a density. So with the example that we achieved here is that fuel is being emitted from a geometry along with the temperature and the density. And the reason why entire concept of the fuel being brought into this simulation is to achieve this kind of moving and living through the air flames. So I could probably achieve very similar result by dealing only with the density and velocity without using temperature, without using a fuel. But it would be more involved, not by a fraction, just by a little bit to get the same look. And sometimes I would, for practical production scenario, I would just go ahead and use only density and the velocity. But for this particular class, since we want to know more about all the grids that available within the fluid container, I will go ahead and recreate it entire simulation utilizing all 4 fields. So the only reason, once again, for the fuel to be used is to let it travel inside of the fluid container, emitting a temperature that would drive velocity vectors, which on its own would drive the density grid. So with this theory covered, let's move on to the example file itself.